Vale, so I'm going to start. Yesterday I saw this slide in the other professor's talk, so I wanted to do it too because it humanizes the guys that you have in front, so I think it's nice you to know me. So that's me. My name is Sidal. Close it. So that's me without glasses or beard. I'm from Argentina, from the south of Argentina. My name is Alfonso. You can call me Al or Alf or however you want. I have a degree in biomedical engineering or bioengineering that I made in the north of Argentina. And 4 years ago, I moved to Barcelona to work in my PhD. So my topic is biomechanic finite element analysis, and I work mainly in fluid structure interaction of the heart. So I like doing stuff. Often there's something else than research. I like to go to the gym, to do Castells. If you don't know what Castells is, just look for 2D 9FM in Google and you will go crazy. Well, I'm gonna talk you today. It's a 45-minute talk, but ask me whatever you want. Just like the first 10 slides have the important information, so everything that is after, I mean, we can skip that. It's not that important. If you want to contact me, you can write me to this email, or you can. My username everywhere else is alfsdg. So I'm going to talk to you about fluid structure interaction in general, because it's what I like, and mainly applied to models of the heart, to electromechanical models of the heart. So, but the first question is why? Why it's important to study fluid structure interaction? It's the same question that you asked your mother when you were young and she take you to English classes and you were asking, why you're taking me to English classes? So why it's important to study fluid structure interaction? So there's a great example of that. This is the Tacoma Bridge disaster. This is a bridge that was too long and too thin and not too well damped, that with a strong wind it started to oscillate and it ended up falling. So of course there was no design of, not any analysis of this bridge. The main theory about this catastrophe was the von Karman did a study, so he suggested that the bridge collapsed due to von Karman resonance. So the bridge, of course, ended up falling, and the next bridge that they built, of course, didn't fall. They looked at twice after building the bridge. So what are the physics behind the fluid structure interaction problem? I tried to make my slides as equationless as possible, but when I showed my slides to my colleagues in the office, they were like, "What? You're not showing equations? Why? What is the problem with you?" So I added some equations, but they are short equations and you probably know them, so they are easy. So let's imagine a flow, right? And you have this bar that can be, I don't know, whatever you want, a straw in the wind or a flower or whatever. And this flow, what it's doing is like pressing this little bar over here, and the bar moves to the other side because it has a flow moving, right? So what is the phenomena happening behind the fluid structure interaction problem? It is nothing else than an interface problem. You have something happening in a surface and some reaction coming back to the other media, right? So the fluid is making a force against the surface of my bar, or whatever you want it to be, and the bar is doing two things. It's making a force against the fluid, and it's deforming. So when the bar deforms, it changes where the fluid moves inside of this cylinder tube, or the fluid domain. So this is the basic phenomena behind our problem. So if we decompose this domain, we can have a fluid domain, a solid domain, and the interface between both domains, that is the contact surface. So in the fluid domain, we are solving the Navier-Stokes equation. You probably know this. This is, well, the way the fluid is described. And in the solid domain, we are solving the linear momentum balance. That is something easy too. This is like the Newton equation. This is mass times acceleration equals forces. This is something simple. And in the interface problem, in the surface, what you're doing is like solving what is logical. What you say is that if this equation over here says that the displacement in the fluid domain should be the same that the displacement in the solid domain. So what does it mean? It means that if the bar deforms in that direction, the fluid domain, where you solve the domain, should be deforming in the same direction too. What you're doing there is imposing continuity of displacements. That's the technical word. And here what you're saying is that if there is a force in this direction done by the fluid, it should be the same force done by the solid. So there should be a continuity of forces there too. So that's logical. Well. So if you call the solid domain equation with an S, because you can do that, what you do is first you solve one of the problems, let's say the solid domain, then you solve the other problem, the fluid domain, and you get back a force, and you can now iterate until you get the solution. So you solve the fluid problem, the solid problem, the fluid problem, and you're done with one of your time steps. You advance your time steps, and you again have a solution for the next time step. So this is the simulation for that bar that I told you before. So you can see the flow with the little arrows moving here inside of the domain. So this represents the flow inside of the tube, and this is the bar deforming due to the force done by the flow. But the thing is that when the bar deforms, the domain where you solve the Navier-Stokes equation also deforms too. So you have to take that into account, because if you don't, you are solving your equations in a wrong manner. So you have the same problem here, but with two bars. It's nothing relevant, but I like it because you can see how one of the bar affects the other bar. So, well, basically that's all I want to say. So now, how do we solve these equations in the computer? You probably heard this a lot of times these days, so I'm going to be brief. As you know, everything in nature is continuous. So, and everything that happens in nature, you have an equation that can model that phenomena that is happening. I don't know, from the pressure of the table in the floor to the light that is traveling from the lights, whatever. So, but the thing, as I told you before, those equations are designed by the nature in a continuous time and space. So everything in the nature is continuous. But the thing is that computers do not understand continuous thing. Computers works in a discrete manner, so they can go to up to a fraction, and they cannot go beyond that point. So what we have to do as a computational physicist is translate those continuous equations to the discrete domain, let's say. So that's the main task of a computational physicist. So how do you do that? Well, you go to a more humble approach. You say, well, I'm not able to solve the continuous time, let's say, the continuous time in the computer. So what you do is you grab your time frame and say, hey, well, let's do this. Let's solve some specific time frames in that continuous time domain that I have. So you have now a continuous domain where you can solve your problem. So I'm not going to solve my equations in every moment in the history of time, but I'm going to solve from 0 to 10 every 1 second, let's say. So that's something that the computer can digest, because that can be solved by a computer. You do something similar for the space. You say, hey, my equations are formulated in a continuous space, but I cannot solve that. So what I'm going to do is grab some point in the space, and I'm going to solve my equations in those little points. And I'm going to be able to solve that because computer can solve discrete points in space. So that's the approach you do to solve these continuous equations in the computer. So, well, that's what I just said. You solve specific points in space and in specific moments in time. So of course you can do something. You can say, hey, something that I can do is like break these little triangles in smaller triangles, and I can approach to continuity. And you can do the same with time, but the thing is that you increase your computational cost. So there is a point that you cannot handle anymore your problem. But the good thing that this is an approach used to see if your formulation is well done. If you go closer to continuity and you get better results, you know that your formulation is right. So that's a technique that we also use to verify our models. So this is a numerical simulation of the Tacoma Bridge disaster. So you can see here the bridge oscillating due to the von Karman vortices that are done here. So the wind is coming in this direction, and the bridge is oscillating due to the vortices. So this is something called elastic fluttering. This can also happen in your plane, for example. You don't want to see this happening in the flight you're going, because that's not good, of course. The plane can crash. I had a longer video, but my colleagues told me that it was too long. So you can find this anyway in YouTube. If you look for elastic flutter, you will see like awesome videos of things getting destroyed. That's what they are awesome. So why I'm talking about this? If I want to talk about the heart, if I'm working in the heart. So FSI also happen in the body, of course, and in the heart specifically. So this is really cool. This is an experiment done by the NASA. They want to test how the human tolerance to wind blast. So they start increasing the wind speed in this guy's face. So this goes like crazy. This is like Mach 0.2, I think, and they go up to 0.6 or something like that. That guy's face is wobbling a lot. So that's, of course, FSI. That's the same phenomenon that it's happening behind the Tacoma Bridge disaster, but in that guy's face. So, but how, again, I want to ask the question, I want to answer the question, why we are interested to do this in the heart? Well, because it helps to design better devices, for example, that can save lives. This is it's not a football match, guys, sorry. And this is an example of, you just take a look to this guy. This guy has an arrhythmia in his heart. He's aware of his condition, so he has something implanted inside that is called an internal cardiac defibrillator. So the guy is like nothing, and in some moment he faints. So in that moment he faints. So what happened there is that his heart stopped. He had fibrillation. So his heart stopped pumping blood, so his pressure dropped, and when your pressure in your brain drops, you faint, because that's the way the brain has to don't die if you don't have pressure in your head, in your heart arteries. So if you want to see it again, in that moment he has atrial fibrillation and he faints. So, but that guy in that moment is clinically dead. He's dead. He had an atrial fibrillation, he doesn't have a pulse, he doesn't breathe, so he's dead. As I told you before, luckily he had an internal cardiac defibrillator, he had a computer under his skin, and he had his heart wired with this computer. He had cables going from the computer to the ventricles and the atria and the outside of the heart. So when this little computer, called ICD, internal cardiac defibrillator, senses that the heart is not beating and that it's having an ventricular fibrillation, what it does is giving a huge shock to the heart. It's not like a pacemaker, because a pacemaker, what does is giving you a small shock, so the heart beats again. So what it's doing here is giving you a big shock, so the heart is fully depolarized again, and it's like rebooted, something like that. So again, the guy faints. So please look at his feet. In that moment, he receives the shock. So in that moment, the cardiac defibrillator senses that the guy is fibrillating and gives a little shock. Why he's moving his feet? Because the shock that he receives makes some produces electrical activity in the muscles of his legs too. So in that moment, the guy makes this little thing with his legs. So in that moment, the ICD kicks in. Let's see it again. So the ICD kicks in. So and now the guy he wakes up alone, and he even asked to keep playing the football. Of course, they didn't. Actually, they kicked the guy off the club, I think. So this is why important to study FSI in the heart. This is something I saw in a little book when I was at the beginning of the year in a company that make pacemakers. They had this mission for the company that this is the most shocking part for me, because this is like why I started studying biomedical engineering, because this guy mission is making devices to alleviate pain, restore health, and extend life. So this is why it's important to study FSI in the heart. So some other examples of FSI in the body. For example, here you have something that you probably saw in your when you were looking yourself at the mirror. This is the carotid artery beating due to the heartbeat. So this is not as shocking as a guy dying, of course, but now after you see yourself in the mirror and see your artery beating, you will say, hey, that's FSI, and you will remind me about me. So this is not as shocking as I told before, but here you have a little bit more blood. This is an artery inside of the brain, and the artery is beating, and the structures around the artery are moving due to the beating of the artery. So that's FSI too. That's the same thing that happens with the Tacoma bridge, but in a less destructive manner. This is completely natural, of course, in the body. Well, this is a case that is special for me, because this is a procedure, a surgical procedure done by this surgeon. That was an Argentinian surgeon that, by the way, he killed himself, shooting himself in the heart due to several things. Take a look at his history in Wikipedia. It's pretty crazy. So in this video over here, you can see FSI in his whole beauty. The heart is beating. They are trying to restore blood flow in the coronary arteries, bringing blood from the left internal mammary artery. So you can even see the blood pumping inside of the coronary arteries, and the heart, of course, is pumping blood to the rest of the body. So this is pretty involves all the things that I told before. So now I'm going to talk about by analyzing the heartbeat. Do you have any question up to this moment, or any suggest, or any request, or nothing? Okay. So as an engineer, what we do to study a problem? You generally cannot treat a problem, the whole problem, with one as a whole. What you do is like breaking the different problems apart. So how we can decompose the heartbeat? The heartbeat is really complex, because you can see, I mean, we are in year 220 almost, and we don't understand still how the heart works, how the brain works. So the heart is a complex system and a complex organ. So what we do is break the different problems apart. Jasmine talked a lot about the electrophysiology. That's the first part of the problem, the electricity propagating from inside the tissue, and this propagation induces the mechanical contraction of the muscle, and this mechanical contraction moves the walls toward the inside of the heart, and this produces a pressure that moves the blood out of the heart. So that's the coupled problem. So if you can solve one of if you can understand and solve each one of these problems, you will be able to understand the heartbeat in a more deeply manner. So these are the other equations that I will show you, sorry. You already saw this one. This is the fancier version of the Newton law. And this is Navier-Stokes equation. That is basically the Newton law for the fluids. But you also have an equation for electrophysiology. Jasmine also explained this to you before. But basically what you have here, you have two components. You have, you know that electricity moves along fluids that has water. So you have a part that is like a diffusive term, that is if the cells were dead, this term will be still active because it's what propagates the electrical impulse without having into account the reaction of the cells. And you have this part that is the reactive term. Technically, it's called the reactive term. That is the reaction of the cells due to the coming potential from the neighbor cells. So this is basically the mathematical problem that we are solving: electrophysiology, solid mechanics, and fluid dynamics. So how do we do to solve this problem? We split it apart. We grab one problem that is the solid mechanic problem and the electrophysiology. You are solving these two set of equations in the same domain because you have the flesh of the heart where you solve electrophysiology and solid dynamics. And you have the inner part of the heart where you solve fluid dynamics. Fluid dynamics, it's more or less a lie because you are also solving the deformable domain because the ventricles deform, so you have to solve that problem too. That's another problem that you have to solve. So we are solving actually two problems here, but let's say that it's just one. So I told you that you have to build this discrete points in space where you're going to solve your equations. So what you do is you grab your drawing of the heart. This is just a AutoCAD drawing of the heart. And what you do is you build a mesh, a computational mesh from this drawing. So what you say, hey, well, I'm going to split this heart in several small pieces, and I'm going to solve the equations in those small pieces. So that's what you do. So, and this is, no, para otro lado. Vale. So this is a, you probably saw this video today and yesterday and every day. So this is the heart beating, basically, the computational heart beating with all this technique that I told you before. You have a slice of the solid domain. I made a slice because if I didn't make the slice, you couldn't see the inside. So this is a slice. You can see the electrophysiology wave moving from the inside to the outside. There is something funny that I just remind that I always have problems. I struggle on how to represent the different physics. You know, flesh is generally red, so I generally represent the flesh with color red. And blood is also red, but water is blue, so I represent blood with blue. So that's something I also do. But I also have the problem with electricity, because which is the color of electricity? I don't know. So once I was talking with a friend of mine, and I asked her, well, which is the color of electricity? She's a graphic designer, and she tells me it's yellow, of course. I mean, Pikachu is yellow, so every electricity is yellow. So from that moment, I always represent electricity with yellow. Sorry. So you have here electricity moving from the inside to the outside, because you know that the Purkinje system, that is the cable that triggers the polarization in the heart, are in the inside. So the electricity moves to the inside to the outside. In both ventricles, you have that phenomenon happening. You have the muscle contracting due to the electricity and the calcium excitation contraction coupling that has been told you like an hour ago. And this solid is deforming the inside cavity. The inside cavity is pushing the blood out of the heart. So that's everything that is happening there. No, it's not necessary that I told you this. So, but something else that is nice that you should know is one of the main problems that I faced when I started modeling this was how to model the heart. When you're trying to model the heart, you have to know very clearly how to define your physical problem. So one of my questions when I started with this was, well, where the heart is, what is the non-moving part of the heart? Where the heart is grabbed to the rest of the body? And I couldn't answer that question. I mean, it was like, where is the fixing part of the heart? So there is actually the pericardium, that is the outer membrane of the heart, is like grabbing the heart, so the heart cannot move to the outside. But what is actually happening is the base is moving to the apex in base apex direction, and the epicardium basically doesn't move. So actually what's happening, the blood is pumped out of the heart because the apex stays fixed and the base goes down. So that's the reason. So you have to represent that on the boundary conditions in your problem. So what we did was like imposing a boundary condition in a problem where we say, hey, epicardium, you cannot move in your normal direction, but you can move in the tangential direction. So that's what you can see here in the apical slice. You can see that there is no, let's start with the base. In the base, you can see that the base is moving in the apical direction and is contracting a little bit in the radial direction, but in the apex, it's happening the contrary. It's basically not moving in the normal direction, but it's rotating. That's something that you want to see in the heart because the heart rotates too. So, vale. So, okay, we modeled a healthy heart. Congratulations, but that's not useful because you want to know what happened. You want to use this for pathologies or for devices, not for seeing what happened. I mean, simulating a healthy heartbeat is also useful, but it's more interesting to model like pathologies. So I'm going to tell you a little bit about left bundle branch block. You know that the Purkinje system, it was triggered the depolarization in the ventricles. So if one of the bundles is broken due to an infarct or whatever, any other reason, you have desynchronized depolarization. What happens is that the impulse is guided through the wires to the right ventricle, but not to the left ventricle. So what happens is that the right ventricle depolarizes and the wave moves to the left ventricle. So you have an asynchronous depolarization. What you have is what normally happens is that both ventricles are contracted at the same time. So, but when you have left bundle branch block, what you have is the right ventricle contracts first and the left ventricle contracts later. And if you don't have a synchronized depolarization, it's a big problem because the heart doesn't beat in an efficient way and you have a smaller ejection fraction and you have a lot of problems. So it's important to have both ventricles contracting at the same time. So here you can see a simulation of that. This is a healthy case. This is the same thing that I showed you before. But here you have a simulation of a left ventricle branch block. You can see that the right side of the heart is depolarizing, fully, but the left side is not depolarizing. So what is happening here is that the wave is traveling from the right side to the left side, and this produces a massive reduction in the ejection fraction, and this is generally, I mean, the patient can probably die if it has this in a very serious manner. So you have to fix this. I know, something else before that. Well, you can see that here. Here you have the normal case, both sides contract at the same time. And here you have the left bundle branch block case. You can see the right side contracting, but the left side is not contracting. And this is, of course, you shouldn't have this. You have mechanical desynchrony. This is the technical name for that. So how do you treat this? You know, put a pacemaker. So what you do is wire again the heart, but you now have control on how the heart is depolarized. So what you do is you sense the electrical activity on the atria, and you sense the electrical activity on the right ventricle. So what you do is you trigger a depolarization in the left ventricle 50 milliseconds before the right ventricle depolarizes. So that's why it's called cardiac resynchronization therapy, because you resynchronize the heart again artificially with a pacemaker. This doesn't make your feet move because the shocks are small. So again, you have the healthy case, you have the left ventricle branch block case. You are seeing it, the left side is in the right because it's a posterior view, so that's why. And this is easier to see the simulation, that's why I done this way. And here you have the simulation with the treatment induced. So you can see that there is an impulse starting here before you have the depolarization of the right ventricle. So with that, what you get is resynchronization of both ventricles, and both ventricles start beating again. So, vale, it's early, so cool. So, I just don't expect you to be an expert in FSI. I'm not. But what I do want is that you see everywhere in FSI in the nature when you go outside into your car and you're traveling and you take your hand out of the window and your hand starts moving. I hope you think about FSI, and I hope you get interested at least in FSI. This is another example of FSI. This is the Buddhist monastery in the Garraf. If you haven't been there, go, because it's a very peaceful place. And these are called praying flags, because when they have prayers written there, and when they move it's like they are praying. So this is very, you have seen this probably in Kilian Jornet movies. So that's all. If you have questions, just ask me anything. If not, we can do the survey pendrive exchange.